So I'm moving towards my first point. I'm recalling the things. So we have started with the MOSFET. So these are the topics related to first unit, and I'm going forward. So I told you that a MOSFET is having 4-terminal device, that is source, gate, drain, and substrate. It is also called as a body. Whenever you are considering this MOSFET is a voltage control device. That gate voltage controls the drain current. If I am increasing gate voltage, the drain current will be more. And that's why I told that this is the active device. Like a BJT, this is the active device, but in BJT, bipolar junction transistor, it is a current control device because base current controls your collector current. But in MOSFET, gate voltage VGS controls your drain current. So this is the voltage control device. Next, that it is a unipolar device. What is meant by unipolar device? That current flowing through this device is because of one type of charge carrier. You know there are two types of charge carrier. First is the hole and second is the electrons. So in this, as I told you, this is the P substrate and there are two N plus dopings present over there. So this is the N type of MOSFET, and there is no channel form. You need to create a channel that you are creating by application of this gate voltage. As higher is the gate voltage, more width channel will get created and more electrons will flow from this to this when VDS is applied. So this is the unipolar device, because in this N channel MOSFET, electron controls the flow of current. That is, there is a charge carrier that plays in the flow of current is the electron. Because of electron, current is flowing. So we have gone through these things. So MOS stand for metal oxide semiconductor field effect transistor. It is having 4-terminal. Source and drain are interchangeable, and W and L is the length and width of this MOSFET. It is a voltage control device because gate voltage controls the drain current. Now, source and drain are interchangeable because the symmetry is same. Here there is N plus diffusion, N plus diffusion. So drain and source are interchangeable. That depends upon where you are applying the voltage. If you are applying voltage at this terminal, then this will called as a drain. If I am applying voltage at this terminal to the N channel MOSFET, then it is a drain for that, and this is the source. And most important thing, that gate is insulated by SiO2 through the channel or this substrate. There is a separation, there is a physical separation between this gate and the substrate through SiO2, and that's why there is a formation of capacitor. Because as you know, there is two plates, and in between that there is a dielectric material. So here the same capacitor is formed. Now there are two types of MOSFET. I told you, that is the enhancement type and depletion type. So what is meant by enhancement type MOSFET? Enhancement type MOSFET means previously it is off. It is open switch, like our day-to-day life you are using switch, like that. It is an open switch. Once I am applying particular voltage, that is the gate voltage, suppose the current will flow after creation of channel, and like color current will flow. So I can say enhancement means when I am giving the voltage, the device enhancement enhances, its performance enhances. And what is depletion type MOSFET? Whose performance deteriorated, means previously without voltage is given, no voltage is given, the device is already on, opposite of our normal switch, and once voltage is given in particular way, suppose negative voltage is given, the device will turn off. Likewise, we will study this in upcoming PPTs. And as I told you, this, as there is a N plus diffusion in P substrate, so there is a formation of two PN junctions. So this is the PN junction formed between this N plus diffusion and substrate. Again, here N plus diffusion and substrate. So there are two back-to-back connected PN junction diode. Now, as I told you, what is the difference between the depletion type of MOSFET and enhancement type of MOSFET? In depletion type of MOSFET, it is also called as a normally on switch. This is normally off switch. Now, here already channel is formed. Means there is a channel. I already given an example of what that is the I need to cross a river and I don't have bridge over there. So first I need to create a bridge, and once bridge is created, I need to apply my force to cross that river. So same way in depletion, what happens? Bridge is already created, means channel is already there. So that's why device is on previously without application of voltage, and that's why current was already flowing over there. But in enhancement type of MOSFET, there is no inversion layer or no channel is there. I need to apply VGS so that there is a formation of channel, and when VDS is applied, current will flow. So this is the normally open switch. Once you are applying gate voltage, formation of channel will be there, and upon the application of VDS, current will flow. So hope you have cleared the thing. That is, enhancement means normally open switch, and this is normally closed switch. And in our this syllabus, we are pointing towards, or we are concentrating on this enhancement type of MOSFET because it is directly related to our normal switch. So this is the thing. This is the symbol, as I in last lecture also told to you that we are using this symbol because there is no arrow, so there is no confusion. Just I told you this is the active high device and this is the active low device. Why? Because bubble indicates whenever 0 is applied to gate, that is logic, low logic is applied, the device will be on. And active high means logic high is given, then device will be on. So just don't interpret in different way, like bubble is given, that's why it will invert the whatever input given. So it is totally wrong interpretation. Just interpret like it is the active low and active high device. So active high means when 1 is applied, logic 1 is applied, device will be on. Active low means when logic 0 is applied to the gate, the device will be on. And I told you this dotted line indicates the device is previously off. When voltage is not applied or input is not applied, device is off. So this is enhancement type, normally open switch. But here this is a depletion type, as dotted line is not there, there is a continuous line, means device is on although you have not applied any voltage. So that is the difference between enhancement and depletion. So we have taken that poll question. MOSFET is a voltage control device, we can recall it. MOSFET is a unipolar device because current conduction is because of one type of charge carrier. So just recall the thing. So in N MOSFET, current conduction is due to the electrons only, and in P MOSFET, current conduction is due to the holes only. So it is unipolar. But in BJT, current conduction is because of P and P, holes and electrons. So that's why it is a bipolar device. Hope you are getting the things, and I'm just going fast because already we have covered that in the last lecture. So enhancement type of MOSFET is act as a like a normal switch. So normal switch is previously open. Whenever you are pressing the button, the device turns on. So it is a normally open switch. So this we have covered. Now, when we have to see the MOSFET basics, how MOSFET acts. So you need to apply certain bias voltage. Okay, like a PN junction, you need to make it forward bias, reverse bias. Same way, you need to apply some electrical field or bias voltage to the MOSFET for making it on. Now, what type of biasing voltage is required? There are two types of bias voltages required. As I have given example that I need to cross the river, I need to create a bridge. So bridge means there is a formation of channel. So that channel will be created when you are applying this vertical field. So I need to apply this gate voltage VGS. Now this will be applied through what? The metal oxide. So what is the thickness of metal oxide? That is defined by TOX, thickness of oxide layer. So my vertical field, sorry, there is a mistake over here, but vertical field is a function of gate voltage VGS and the thickness of oxide. Same way, only bridge forming is not sufficient. You need to apply force because bridge is created. I need to cross a river. By standing over there, I am not able to cross the river. So I need to apply my force. So current will flow only when there is a potential difference across it. So Now electrons are present over here, channel is formed, so there is electrons present over here, and whenever I am applying VDS, drain to source voltage, D is positive and source is negative. Just remember this thing. So as there is a potential difference between this source and drain terminal, electron will move. Now electron will move from source to drain and current will flow from drain to source. So always remember, flow of electron will be opposite to the flow of current. Now, as I told you, and we will be discussing this in the coming lectures, that source and substrate. The substrate is also called as the body. It is also called as a bulk. It is also called as a substrate. So this is internally connected to the source to avoid a body effect that we will see in the coming lecture. So just remember this thing in your mind. Just keep that in your mind. So as I told you, first thing you need to apply the gate voltage to create a channel. So I need to create a channel. So gate voltage is required, and for the flow of current I require VDS. So there are two types of voltages. One is the vertical field and second is the horizontal field. Horizontal field is related to the VDS and length of the channel, because this is the VDS I need to apply and it is applied for the length. So it is a function of VDS and length. So going towards the basics. Now, how N-channel enhancement MOSFET will work. So this figures already I have shown you. Just I am using it again and again so that at that particular point there should not be any deviation. Means I need not have to move here and there. So although these diagrams are repeatedly coming, so don't get hesitant because of that. So here at start I told you you are having the MOSFET. So for clear understanding, just I am switching to this paint. Hope you are everybody is able to see this paint view. Now I'm just trying to draw this diagram in paint. So what MOSFET is having, it is having P type of substrate. Okay, so I am having P type of substrate over here, so I'm writing here P substrate. Now what next thing you are having two N plus doping. So I am having these two N plus doping, one over here and one over here. Okay, so I am writing over here, this is the N plus doping and this is also a N plus doping present over here, which forms your source and drain terminal. Now what is the next thing you are having? There is a oxide layer, because gate terminal is insulated by SiO2 layer, so it is not directly connected to this substrate. So this SiO2 layer is present over there. So this is the oxide thickness. Now I'm just drawing this particular source terminal. So this is my source terminal, and second that I am having this drain terminal, as you already learned. So there are total 4 terminal. First is the source, drain, this is my substrate. So this is substrate, I'm not giving the notation now. And here there is one plate which is firm, metal plate, so that I can take out the gate terminal. So this is my gate terminal which is connected to this SiO2. So I can write over here, this is my gate terminal. I'm not able to write over here. Hope everybody getting. It is very difficult to draw over here. If the board was there, I could have done in better way. But this is the just for your understanding, I am drawing this diagram. So now there is a formation of this parallel plate capacitor. One plate is acting as a gate and second is this substrate. Now, as I told you, in P-type material, majority charge carriers are what? That majority charge carriers are holes. I'm just drawing hole like this, just bear to this. So these are the holes. So I am having lots of hole present in the P type of material. So that are over here. And what are the minority charge carrier present here? That are electrons. So I'm drawing electrons like this. Okay, so there are less number of electrons but more holes are there. So just remember what I have drawn. This blue indicates hole and this black indicates electron. Now at start I told you that this source is grounded and this is connected to what? It is connected to substrate to avoid a body effect. So I am connecting this to uh, this, and this is consider it is grounded. So I am considering this as a grounded. Now when I am applying certain gate voltage VGS, here I have applied gate to source voltage. What will happen? Because of positive charge, it will attract electron inside this P substrate. So what are the electrons present over there? It will get accumulated near to this surface and holes will get repelled inside the substrate. Okay, so there is a formation of this inversion layer. This is because of electrons which will get attracted because of whatever the gate voltage is applied, and that's why there is a formation of channel which was previously not present. So whenever you are applying proper gate VGS, gate to source voltage, there is a formation of inversion layer. Now as I told you that it is a voltage control device, means if I am applying VGS more and more, means more and more width channel will get created, and if the width of channel is more, means you are having more electrons in that region, and if you are having more electrons in that region, means current will be more. So is it proved that if I am giving VGS, depending upon VGS, I am able to control my gate current? So hope you got the things properly. So I'm switching over my PPT. So here at start there is nothing over here. There is a two PN junction as I told you, and that's why there is a formation of depletion region. So here it is not mentioned, but just remember that there is a depletion region near this PN junction. After that there is no current flowing because there is no channel, and that's why there is no current flowing. Now what happens when I am giving certain VGS? So whenever I am giving VGS, as I have explained in that paint, more VGS you are giving means more electrons will get attracted from P substrate and there is a formation of channel over here. So here you need to apply VGS in the way that it should be greater than VT. What is VT? Here you can say VT as VTN also, because I'm telling you in terms of MOSFET, N type of MOSFET, N channel MOSFET. So VT is called as the threshold voltage. As in the case of PN junction diode, you need to overcome the forbidden voltage, that is 0.7 for silicon and 0.2 or 3 for germanium. That may vary depending upon book to book. So I need to apply VGS greater than VT, which is the barrier voltage, to overcome the depletion region, where in depletion region you are having the immobile charge carrier. Current will not flow because of immobile charge carrier. It only flows because of mobile charge carrier, which are electron and holes. So in this case, for N channel, I require electrons to flow for the flow of current, because it is a unipolar device. I already told you. So I have to apply VGS greater than VT so that there is a formation of inversion layer. And now just tell me, what is the voltage VGS present over here? It is nothing but a whatever VGS you have applied, because this is grounded. So VGS is nothing but a VGS over here. Now what is the voltage at this VGD? Just think over that. What is the voltage at this VGD? It will be same as VGS. Why? Because this drain is also connected to ground and the source is also connected to ground, means these are at same potential. You have applied VGS as a gate voltage, so same voltage will be present over here, because with respect to gate and drain. So now because of that reason, this depletion region is uniform all over this region. Okay, the width of depletion region is same throughout this channel, because voltage at this point is same as VGD. So when positive voltage is applied, electron will get accumulated near the surface, and there is a formation of inversion layer when VGS is greater than threshold voltage. And once inversion layer is formed, now it is ready for current to flow. Now, how current will flow? Hope up to this the idea is clear. Now, next thing. In previous case, we have only think of this VGS voltage and we have not given any drain to source voltage, because I told you bridge is created. Now you need to apply a force to cross the river. Now here electrons are there, but until and unless potential difference is not applied, they will not move. And that's why I need to apply certain voltage VDS, which is small. Here it is not mentioned it is 0.1, 0.2, but it is small. It is less than whatever VGS is applied. Okay, so suppose VDS is applied, what will happen because of that? Voltage at this point VGS is different than VGD, because previously this source is also at ground and this was also ground, but now you have increased the VDS, and that's why what will happen at this point, the voltage will be more than this point. And because of that, what will happen? As you know, this is a PN junction diode. Already I have shown the diagram. So this PN junction diode become forward bias or reverse bias now? Just think, because this is the N type of material and this is the P type of material. P is connected to what? Already it is connected to ground, and this N is connected to positive, means this is becoming reverse bias. And if it becomes reverse bias, means depletion region increases, as per your previous knowledge of the semiconductor devices. And that's why at this point this depletion region increases, which is shown over here. Just see, as you are increasing the VDS more and more, because this particular PN junction become reverse bias, and this is already as it is, so there is no effect of that voltage on this, but this depletion region increases. So what happens? When VDS is applied, there is a potential difference across source and drain, and that's why electron will flow from source to drain. So current ID, or we can say IDS, whatever written, it is same. Drain current or drain to source current. The current will flow. The current is proportional to the number of carrier in the induced channel. As I told you, if you are giving more VGS, more electrons will be accumulated over here, and more charge carriers are present, means current will be more. The channel is controlled by effective voltage. What is the effective voltage of this channel? That I am giving VGS, but what is the effective voltage? I need to first overcome VT, threshold voltage, because although suppose VT is 0.3 and I am giving VGS as a 0.3, 0.3 will get cancelled. Still you have not given any voltage. If you are giving more than that, so it will overcome the barrier, and then there is a formation of inversion layer. So that's why effective voltage is nothing but a VGS minus VT. When you are giving VGS greater than VT, threshold voltage, suppose it is 0.7, then after 0.7 there is a formation of channel. Before that there is a forbidden gap, depletion region. You need to overcome that. This already you are studied in the PN junction concept. Now the electron charge in the channel due to this effective voltage is what? What is the charge? Q equal to C into V. That is capacitance and the voltage. So same is mentioned over here. Q always, as this is the electrons, mean negative charges will be there. So I have to write minus also, but here it is mentioned more. So COX is what? Oxide capacitance. Because of this SiO2 layer, what are the oxide capacitance? That is there. WL, width and length of this device, and VOV, that is the effective voltage that is given. So charges is directly proportional or equal to C into V. The gate capacitance COX is defined as capacitance per unit area, that you already know. And in this region, what happens? As I am increasing the voltage VDS, my current also increases. So this is a linear, means it follows the Ohm's law. As voltage increases, current increases. That again in detail I will tell you by showing the characteristic graph. Now, this thing is very important. You need to remember anyhow. That is, what is the drain current? Because in every region, or as I am changing the voltage, characteristic will get changed. So there are three different regions of working of MOSFET. Just remember, there are three different regions of working of MOSFET. One is cutoff region, where your device is off, no current is flowing. Second is the linear region, in which this is the linear region where we have applied VGS greater than VT and some small amount of VDS is applied. So current increases as you increase the VDS. Okay. And third is the saturation, where it is the last stage. Whatever you do, whatever type of voltage you are applied, there is no effect of that on the current. Current will be insaturated. Like an example of mixing salt into the water again and again, like that you better know. So this, just remember, current, drain current in linear region is equal to mu n. What is mu n? Mobility of electron. Because I have written suffix n over here, meaning of that, as this is the n channel, so here mobility of electrons is considered. COX is what? Capacitor, oxide capacitor. W by L ratio, that is width and length. VGS, now as you know, this current ID depends upon VGS also and VDS also. So these terms are coming over here. Anyhow, you need to remember this, because your VGS effective voltage should be this, VGS minus VT, and you need to apply VDS so that electron will flow from one side to another. So this is very important, and depending upon this we can find our saturation current. There is no need to remember saturation current formula. So just remember this drain current in linear region. So hope you are getting the things. So in this region where VDS is small, which is applied, the device is acting as a linear resistance, whose resistance changes with the application of voltage. Now, next and the last step of the operation, that is, I told you, in saturation region. Up till now we have seen cutoff, where the device is off, linear, where it acting as a variable resistance. Current increases with increasing VDS. Now here in saturation region, what happened? Now this is very important. Just concentrate. This concept will be useful in channel length modulation also, which will be the next topic. Now, as I have previously, here there was a channel which is throughout over here, and it is having same width. But now this is tapered at the end of drain. Why this is happening? In previous, we have given VDS small, and I told you that PN junction becomes reverse bias, and that's why depletion region increases. Now, if you increases VDS again and again at particular limit, that is VDS saturation, that VGS saturation is VGS minus VT. Always remember, VDS saturation voltage is VGS minus VT, where that voltage is greater than VGS voltage. So what will happen? This PN junction will become more and more reverse bias, and if that becomes more and more reverse bias, there is a depletion region is more towards the drain than the source. Agreed? So here the depletion region will be more, and because of that, what happened? This channel will become tapered near to the drain surface, because as we are increasing the VDS again and again, voltage at this drain point will be more than this point. Here it is zero only because it is connected to ground, but here I am increasing. That's why voltage near to drain will be more as compared to this, and that's why channel is more over here and tapered over here. Now, what is pinch off? This point is very important. Now, before going to pinch off, just I am reading this. As VDS increases, previously it is small, but now it is increases from 0 to VDS. The voltage between gate and the point along the channel decreases from VGS at source end to VGS minus VDS at drain end. Here it is VGS only, but here it is what? I need to find out VGD. What is VGD? VGD is nothing but a VGS minus VDS. So as VDS is increasing, meaning of that this voltage is increasing. Okay. Now inversion layer depends upon what are the voltage difference across MOSFET structure is, and that's why as voltage difference is more and voltage is more over here, this particular junction become reverse bias, and that's why diffusion region increases and this become tapered near drain. As this is tapered, previously I am having full way to go, now it is just shortened or tapered, means it is bottleneck will get created over here, and that's why meaning of that electrons are there but it is crowded over there, and that's why resistance increases. So the resistance increases, and as resistance increases, previously current was increasing like this exponentially, now it is somewhat reduced. So your current id reduces instead of increasing, that what done in linear region, now it just start saturating as VDS is increases. So here as this increases, the resistance of the channel increases and drain current decreases. Now when your VDS, this is very important, just concentrate, when VDS is equal to VGS minus VT, what? When VDS is equal to VGS minus VT or greater than that, what will happen? That point is called as a VDS saturation, where your channel is only connected, means it is tapered in such a way that it is only connected to this particular region point, and that's why this point is called as a pinch off region. What is pinch off region? The pinch off region where when VDS is equal to VGS minus VT, the channel will get tapered and it moves toward the source. Previously it was parallel, means it was having same width, but now it is shifting over here. Again if I am increasing VDS, again it will shift like this, that this will become more and more tapered and channel moves toward the source. Understood? So increasing VDS beyond certain value, there is no effect on drain current. That channel becomes vanished and it will shift toward the source and resistance will be more, and that's why current will not increase. So ideally there is no effect of your VDS on drain current in saturation. Again I am repeating this point, this is very important. In saturation region there is no effect of VDS, that is drain to source voltage, on drain current. Means your drain current is independent of your VDS. I am increasing VDS again and again, there is no effect, my current is already saturated, so it will not affect my current. So what this is called as a, this is called as a constant current source. What is constant current source? Constant current source means the current will remain constant whatever may be change in voltage. So same is happening over here. So in MOSFET, when the MOSFET is in saturation region, it is acting as a constant current source. Hope you are getting the things. So pinch off occurs means when VDS equal to VGS minus VT, at that time the channel is shifted towards the source, and that point is called as the pinch off. So here it is point is connected and this is called as the pinch off point. If I am increasing VDS again and again, this pinch off point will shift towards this source and channel resistance increases. Now what is the drain current in the saturation region? So drain current in saturation region is denoted by same way as written in the linear, but here what is written? VGS minus VTN square. And I told you, you do not have to remember this formula if you know the previous formula. So when this saturation region occurs, when your VDS is equal to VGS minus VT. So if I am putting instead of VDS in the previous equation as a VGS minus VT, I should get this. So just see, this is the formula of drain current in linear region. And in saturation region, what happens? VDS is replaced by VGS minus VT. And if we are replacing VDS equal to VGS minus VT, what will happen? Just substitute, you will get this particular equation. Do it on your book. It is simple, just you need to cut VGS VT so that you will get this particular equation. So up to this, hope the idea is clear. Now everything on a single page. Just listen carefully, those who didn't understood previous thing. So at start, I am having this P substrate. There are two N plus dopings. It's from source, drain, gate, and substrate. Now, when I have given VGS greater than VTH, that is threshold voltage, there is a formation of inversion layer because of electrons will get attracted because of the voltage VGS is given, and holes will get repelled to the substrate. So there is a formation of inversion layer. So this is width is same all over the channel. Now what happened when, and here just remember I have not given any VDS. Now suppose in second my VGS is same, that is it's greater than VT, the channel is formed, but now I have applied certain VDS, and because of that what will happen? This PN junction at this side becomes reverse bias and there is a depletion region and it will taper your channel. So previously it was parallel, but now it is tapered at the drain edge because voltage VDS at drain edge is more. Now when it is equal to, now this is what VGS is less than VT, means VDS is small, it is less than VGS minus VT, and this less than equal to greater than, that is very important. So pinch off occurs when VDS is equal to VGS minus VT. Just remember, equal to. At that point what happened? This is just connected to drain. Okay, previously there is some large part is connected to drain side, but now it is just a pinch off, means only part of that is connected to drain. And that's why at this point what happens? The resistance is increasing and that's why current decreases. So here previously it is off state, now as VDS is applied, current is increases linearly, it is acting as a linear resistor. After that, if this happens like this only, it will go like this. But now because of this pinch off, there is a curve present over here. This is because of pinch off. This happens why? Because your VDS is equal to VGS minus VT. That is VDS is saturating. So because of that, this channel is less towards the drain and it is more towards the source. Now after that, last step, that VDS is increased more than VGS minus VT. What will happen? The voltage at this drain terminal is more and more. That's why this is becoming more and more reverse bias, and that's why depletion region will be more, and it will force electrons to move towards the source side. So channel is shifting towards the source. Previously it was at the drain also, but now as the voltage VDS is increasing again and again, it will move towards the source. Now one thing I just want to know from you, just tell me what is the voltage at this point and what is the voltage at this point. Which point you called it as a pinch off region? Answer to that question, just concentrate. Always pinch off region will be at this point only, because at this point your VDS is equal to VGS minus VT. But as VDS increases, the voltage at this point is increasing again and again. It is more than VGS minus VT. So pinch off point, at pinch off point, always your voltage is VGS minus VT. And at this point, and at this point, it is always more than the VGS minus VT. So this thing, just keep it in mind. And this is the current where in saturation region, it should remain constant. Actually, practically, it doesn't happen. That is the effect of channel length modulation. That is happening like red curve you are able to see. But ideally, there is no effect on drain current on the drain voltage on the drain current. So as you are increasing VDS again and again, this drain current will remain constant. So in this way, the N channel MOSFET characteristic is divided into three regions. First is what is the cutoff region, where VGS is less than VT. Just remember this wording, that greater than, equal to, less than. Just remember that VGS is greater than VT, then and only then current will flow. Before that, means when VGS is less than VT, the current is flowing because of minority charge carrier, leakage current, subthreshold current, likewise, and that's why that current is very negligible. So this is in the cutoff region. First region is what? Cutoff region. After that, I have given VGS greater than VT, and because of that, there is a formation of inversion layer. And one small amount of VDS is applied. So this is VDS is applied, current will start flowing. So current increases with increasing voltage, that is VDS. So this graph is in between ID versus VDS at constant VGS. Just remember ID versus VDS at constant VGS, because there are three parameters involved over here, and that's why one is taken constant with 2. So this is called as a VI characteristic. What? So this characteristic is called as a VI characteristic, which is the characteristic between ID and VDS at constant VGS. And second characteristic is related to ID versus VGS. Previously we have taken VGS constant. Now we have taken VGS variable, but we have taken VDS constant. So when the graph is in between ID versus VGS at constant VDS, it is called as a transfer characteristic. Understood the difference between VI characteristic and transfer characteristic? In VI characteristic, it is a graph between ID and VDS at constant VGS. And in transfer characteristic, it is a graph between ID and VGS at constant VDS. So here, that is the cutoff region has been done. This is the linear region where you are giving small VDS. And last is the saturation region where you are increasing VDS in such a way that pinch off occurs, and after that pinch off, the curve decreases. So instead of having the habit of increasing, it is now start concentrating. So when VDS increases again and again for the constant VGS, your current remains constant. There is no effect of that VDS on the ID, that is drain current, and that's why in this region, in saturation region, MOSFET is acting as a what? Constant current source. Hope this idea is clear to you. So same is mentioned over here. So just tell me, just is a general question. Now there are three types of characteristics, I mean these types of region you are able to see. So in cutoff region and saturation region is used for what? In which application you can use cutoff and saturation? Think over that. So if I want to use transistor as a switch, I can use that in this two region, that is cutoff means off and saturation means fully on. So for that application, you have to work this transistor in this two region. Now next application that everyone know, that is the amplifier. You know amplifier, whatever signal I am giving, I need to I require same signal but having the amplitude variation, that is increasing amplitude. Size should be same, shapes should be same, but I want increase amplitude. So in that region, if for that particular application, in which region that transistor should work? It should work in the linear region. So always when you have to work transistor as a amplifier, it should be in the linear region. In linear region, your current increases with increasing voltage. So hope this basic also get cleared. For switch, it should be working in a cutoff and saturation region, and for amplification or amplifier circuit, it should work in a linear region. So this equation, as I already told you, in linear region, it is dependent on VDS, VGS, that term. But in saturation, it is acting as a constant current source. It is independent on your VDS, and that's why this VDS term is not present in this saturation current equation. Just remember this thing. These are the things you need to remember, so that at the time of writing you will get clear. Yes, VDS is will not be present in saturation because it is the constant current source. It is independent of VDS. My current ID is independent on VDS. So hope you are getting the things. It is not going tangent or about that. So read the things again. If you are having any